Yeah, so essentially what is covered for the second tutorial group is that we are now considering the combination of functions. So functions can be combined together, okay, because they can be functions of functions. So this is an example of what they are, okay. So you can sum or subtract two functions, can multiply two functions, can divide functions, right? And essentially there's actually more combination methods than just the three shown here. Okay, you can have f of x to the power of g of x as well, right? And we'll certainly address them in the future. So, but also what's important here is that the resultant function y of x, which is the combination of functions here, right? There are some requirements, and that is right. The domain for the resultant function is the intercept of the domains for the constituent functions. Okay, and that only makes sense because you have to have the constituent functions, or rather the input functions, being defined, right? If f and g are defined, then y can be defined, okay? So certainly you cannot have just one of the functions being defined in a certain domain and expect the output to be defined as well, okay? So for example, if g of x, right, is not defined at, for example, x more than 0, then you cannot expect you take something that is undefined, multiply by f, and you get something out, okay? So as one of the constituent functions is undefined over certain domains, right, then certainly the resultant will also be undefined, right? So then the quotient function here, right, we have an additional requirement that g of x cannot be 0, or else it wouldn't be defined, or else y wouldn't be defined. So then I've gone through some examples here, okay? So essentially you just have to investigate the domain of f and domain of g, find the intercept, and then just apply to the individual functions, okay? So then we are going to continue on the function combination by looking at function composition. So composition is really just putting one function into the other, right? So much so that you have this machine of a machine. So if you have an input variable x, the input feed into the first machine, f of x, you get some output. Then that output, right, you feed into the second machine, let's say g, and then you have an output variable. Okay, so therefore one can write y, right? Y is g of f of x. Okay, so therefore one way to write this variable y here is y. You can see that this is a g, so g is the outer function, then of f, then f takes in the input x. Okay, so this is what a composition function or composite function is about. Okay, and this is a big deal, right? Because we don't usually have just one operation being applied to inputs at one time. Okay, in the real world, we are always, you know, like in the manufacturing of a product, for example, okay, there are many intermediate processes, right? So from the raw material, you feed into some manufacturing process, then after that you take the output of the manufacturing process, feed into another manufacturing process, and so on and so forth. Okay, so function composition is representative of the real world, and it is also very representative of the machine learning neural network. Okay, the machine learning neural network is actually a humongous composite function. Alright, so we're going to look at that later on. I mean much later, like Math 3. So therefore, let's look at a simple example first. So let's say if you have f of x equals to root x, g of x equals to x squared plus 3, right? So certainly, if I define a y1 of x, which is g of f, then you can see that actually, you just have to treat, this one I've mentioned many times before, and that is right. If the input is x, then you just look at the input x in the expression. So now the input what? The input becomes f. So you just put the whole f into the same expression, replacing x by f. You can see the similarity, right? X squared plus 3, f squared plus 3, right? It's the same. Effectively, it's the same function. So then after that, you just sub the whole f into the expression, and therefore you get x plus 3. Okay, the same goes for y2. y2 is f of g, so therefore it's really just root g, right? Because f is just the square root function. So you put the whole g inside, so therefore you get root of x squared plus 3. Okay, so this one nothing much, it's really just substitution, which I think many of you have done before. Okay, so then maybe a little bit complicated will be on the domain of the resultant function f. Okay, defining the function is not so big a deal, but however, the domain has a bit of complication, and that is right. Okay, so this sentence may seem a little bit of a mouthful, right, but I'll explain it in more layman terms. So it says here that the domain of y, the resultant function, has to be the set in the domain of f, for which f is in the domain of g. Okay, so that doesn't make sense to most of us. So what happens here is that it's actually very straightforward to define. Okay, you see, what is domain? Domain is x, ma. This domain refers to x, right? The x values for which the function is defined. So which means we are looking at x, right? So you can see here, the domain for y, which refers to the x values, must be the domain for f, what? Because x is fed into f. Okay, but there's a catch. And the catch is, right, f got to be defined, right? Because f is to be fed into g. So this is what the second expression here means, right? For which f is in the domain of g. So that's the deal here, right? So practically what we do is simply to check, first of all, what is the range of f. Now, is the range of f in the domain of g? So basically, from this part, we can write check if range of f is in domain of g. Okay? Now, if yes, then the whole domain of f is the domain for y. So basically, there are two conditions. Yes. So first condition, yes. So if the whole range of f is in the domain for g, and if the answer is yes, then domain for f, or rather domain of y, right, equals to domain of f. Okay, because the whole f is defined in the domain of g, what? It's a subset, right, in the domain of g, which means that g can take all of f. So if that's the case, right, then the domain of f must be equivalent to the domain of the output function. Okay, since you can always calculate f in that domain, and then you output the range, then the range is always in the domain for g, so g can accept all values of f. So there are no constraints, right, in other words. So therefore, the domain for y, right, must constitute the whole domain for f. Now, of course, that's yes. Then what about if no? So second condition, no. Okay, so what does no mean? No means, right, the range of f exceeds the domain for g. That means some part of f values is outside the domain for g. So g cannot be defined, what? So what do we have to do? Constrain the range of f to the domain of g. So if no, right, then we have to constrain domain of, the range of f to domain of g and solve for the restricted domain of y. Okay, so constrain range of f to domain of g and solve for the domain for y. Okay, so much so that your g can be defined. Because your y is basically g, what? You can see here, right? So of course this is quite a mouthful, especially for the second point. So I'm going to demonstrate in the examples later on. If you don't understand now, it's totally fine. Okay, but I think point one is quite straightforward. Okay, so I made a point here that you cannot evaluate the domain directly from the resultant function. Okay, because the resultant function does not consider the domain for the input function f. Okay, so now let's make an example from here. Now look at this guy. You can see that the range of f, right, the domain for f is x more than and equals to 0. Can you see, right? So 0 positive, that's the range of f. Okay, then what about the domain of g? So the domain for g, right, is r, because x squared plus 3, right, is just a smiley face. Right, so we know that polynomials, the domain is everywhere. So which means, right, this range is inside this domain, so it belongs to point 1. So therefore, this is point 1. Okay, so this condition is point 1. So the answer is yes, the whole range, right, is inside the domain. So you can see that the domain for y1 of x, right, is simply the domain for f. There, it's exactly written here. Okay, so it makes sense because in order to define your f, your x must be defined. So x has to be 0 and positive, right? Which is the domain. I mean, the domain and range here in this case is the same. Okay? Then, as long as x is defined, then you have your y1 being defined. So therefore, the domain for f must be the same as that for y1. Okay? And then you can inspect. If you were to evaluate the domain for y1 directly from this resultant function, which is x plus 3, what would you get? You will get R. You will get R. Okay? Because R, right, is the domain of y1 equals to x plus 3. Okay? If you evaluate directly. If you evaluate this directly, then you realize, hey, domain is R what? Because x can be anything. Okay? So imagine you putting a negative 2 into x. But if you were to put negative 2 into x, you think you can calculate, but actually x, negative 2, have to go inside f first. Then you try to root negative 2. Not possible. Okay? And this is also evident in Desmos. So Desmos also does understand that you need to have these conditions. So let me demonstrate that. So you type in square root x for f. So this guy is x squared plus 3. Okay, so you see the two curves there. So let's say your y is g of f of x. So you do realize that Desmos understand that because this is a function composition, okay, and you have to look at the input function f, right, which is the domain. So the domain is actually x more than or equals to 0, right, following this red curve. So therefore, even though you have x plus 3, right, as your resultant function, oops, sorry, my bad, this should be square. Okay, so Desmos understand that even though your resultant function is a x plus 3, but the domain for g, as you can inspect here, right, is only 0 or positive. Correct, correct. You must see the constraint. Okay? So certainly if you were to like define y of x equals to x plus 3, then obviously it will be the whole domain of R what? Okay? Even though both of them are the same function, but the domain is not the same. Okay? So you can inspect the actual domain using Desmos for composite functions, right? During your practices. Okay? So let's take a look at more examples here. Right, so I'll go through directly to assist your understanding. So you have a p of x which is f of g here, right? F of g. So therefore this will be equivalent to root. So you can straight away root. So you can see this is x, right? So you replace all the x's in f by g. So this is really just g minus 1. So then you just substitute g into the expression. So it's really minus x squared minus 1. Okay, so this G, make it in blue. Is that right? Okay, then apparently you have a problem, right? What's the problem? Now, let's evaluate the range of G, because the inner function is G. So, range of G, so what's the range of G? Minus x squared. So, which means that x squared, 0 or positive, minus x squared, 0 or negative. Right, because we know that minus x squared basically look like a set face, right? With the vertex that is at the origin. Okay, this is your G, right? So therefore, you know that the range of G is really 0, sorry, I should say that this is minus infinity all the way to 0 inclusive. Okay, because it can be 0. Okay, 0 squared is 0, right? But then if you look at minus infinity to 0, what is the domain for f? Domain of f is x got to be more than or equals to 1. 1 positive infinity. Correct or not? Because x less than 1, then we're in trouble. Right? We cannot square root that negative number. And then you immediately can compare. Minus infinity to 0 is entirely not in the domain of 1 to infinity. Therefore, range of G is entirely outside of domain of f. So P of x is not defined because the domain is the empty set. Is that right? Okay, so in other words, right, this function, there's simply no x. There's simply no input for which you can calculate a number out. That's the takeaway from the analysis here. Is that right? Okay, so that's for A. Now about for B. So let's look at B. So this B, right, is equivalent to g of f. So g of f in this case will be minus f squared. So minus f squared is simply squaring this root. So therefore is x minus 1, right? So it's really minus of root x minus 1, but whole thing square. Okay? So basically you just need to remove the square root. So hence you get minus of x minus 1, which is 1 minus x. Is that right? Okay, so 1 minus x seems to be a linear function for which the domain is R. Okay, but as we have illustrated, we cannot just identify directly from the function. So we have to analyze. Okay, so what do we do? We do the same thing, right? So therefore, what's the domain, what's the range of f? Range of f is what? Range of f, because root, right? So it can be 0 or positive. 0 or infinity, 0 to infinity. What's the domain of g? Domain of the outer function, So domain of g is domain of g is R, because you can fit anything into g and still calculate the number out. It's just a set face looking curve. So you notice that the range of f is entirely in the domain of g. So that belongs to the first condition, what? Okay? Therefore, or rather since range of f is in domain of g, so the domain of q equals to the domain of f. Okay? That means it must be equivalent to the domain of the input function, this f function. So that's for B. Okay? So this is basically condition 1 shown here. Right? So maybe I just put a note here. So this guy is actually condition 1. So let's take a look at the last problem. So the last problem is f of f. So composite function of itself. Okay? So r of x. So you can see f is here, right? So it's really just the root of f minus 1. But the root of f minus 1 is just the root of f minus 1. I mean x minus 1. Root, then this guy, root again. Then you put the whole function in. So it's so it's x minus 1. Minus 1 outside. So this is the function. The root of x minus 1 minus 1. Is that right? Okay. So same thing. Just do the same analysis again. Right? So what is the range of f? Range of f, we know what? 0 to infinity. Range of f is 0 to infinity. Then what about the domain for f? Domain of f is 1 to infinity. Okay, here comes the second condition. Okay, so you notice that the range is 0 to infinity, but the domain is 1 to infinity. So 0 to 1 is not inside the domain. Is that right? Okay. So now you got to constrain. So this is second condition here. Constrain range of f to domain for g and solve for d of y, the domain of y. Okay, but because you got f of f now, right? So hence, let me write. So this guy, this guy belongs to the second condition. Okay. So therefore I've got to constrain already. Okay. So I have to constrain what? I have to constrain the range of f to the domain of f now. Okay? So let f of x be more than and equals to 1. Okay? Because you've got to constrain the range to the domain Because domain is what? Above 1 ma, 1 or more. So therefore that f of x be more than or equals to 1. But what's f? F is just the root of x plus 1. Oh sorry, x minus 1. More than or equals to 1. Okay? So therefore if you notice x minus 1 must be more than or equals to 1. So x must be more than or equals to 2. Is that right? Okay? So therefore, you can write the conclusion. Therefore, the domain for R is 2 to infinity. So this will be the result. Okay? So basically this part is the part whereby you need to constrain R of f to D of f. Is that right? Okay, so this will be the end result here. Can ah? Okay, so let me demonstrate that Desmos exactly tells you the same thing. So you can see f of x, right, is root x minus 1. So what happens if I put, let's say for example, R of x equals to f of x. Now you see what happens to the blue curve? You see? So f, right, the domain is 1 or more, 1 to infinity, right? But R, which is f of f, as what we have worked out earlier on, okay, you can see the function actually is defined from 2 onwards. So which is exactly our result here. Okay? Yep, so that's for the composition of functions and their domains. Any questions? So you probably need a few practices to get used to this. Next, important, inverse of a function. So what's the function inverse? Function inverse is exactly what it says, which is like a reverse engineering process for which, right, from the input you put into a machine, F, to produce some output. So let's call that machine a production machine. Okay, so input to output, right, goes through a machine F. Now imagine that you want to get the original input from that output. So therefore there must be another machine that you can feed the output into such that it will reverse whatever this machine has done to get the original input. Okay, so therefore the reverse engineering machine is called the inverse of the function, F inverse. Okay, so from here, it's pretty easy to see that, right? Y is f of x. Y equals to f of x. So what's x? X got to be f inverse of y. Simple as that. Okay, because f inverse of y, right, you get back x, what? So we can write this, what? X equals to f inverse of y. Okay? So which is why we have the first condition here. Which is why we have this condition. Why? Because the y just fit in this guy. So isn't this x, right? F inverse of f of x. So f inverse of f of x, obviously you must get back x, what? Why? Because it's like you do nothing. You produce already, right? Then you fit into the reverse engineering machine to get back x. So it's like you do nothing lah. Maybe you are testing your machines, that's all. So what about this guy here? Then obviously you can put x into here also, what? So therefore this guy can also be written as f of f inverse, because x is just f inverse of y. So in some sense it's also that you are doing nothing. Okay? So therefore you get this guy. But what's the important takeaway? The important takeaway is that, right, the function inverse of the function will return you back the original input. Okay? You can see that. Right? Same thing. Function of the function inverse, right, will return you back the original input. Okay? Because that's the definition of a function inverse, because you are reversing the process. Okay? So you must get back the original thing. So what is the inverse function of f inverse? What is the inverse function of f inverse? That means I want the function notation. Anybody can tell me? You have a function called f inverse. Now I want the inverse of that function. What is that? F of x. Very good. Okay, so the inverse function of f inverse is f inverse inverse. So it's the inverse of f of x. So therefore this is really just f. Okay? Because it's like you reverse the reverse engineering machine. So therefore, you'll get back the production machine. All right? So it's just kind of consolidating your understanding of what is really the inverse function. So there are some inverse functions that are intuitive to evaluate. For example, if you have the squaring function, then the inverse function must be the square root function. There's no way around that. Okay, if you square some input, right, then what is the inverse function? Must reverse the squaring process, what? But you know, inverse squaring process means square rooting process, what? Correct not? So square and square root, they are inverses of each other. Okay, very simple. So this is by intuition. So now, if you look at the mathematical satisfaction, right, it does work. Okay, so F inverse is root. So root of F, but F is x squared. So root of x squared. Obviously, you get back x. Okay, so as we mentioned, right, x must be obtained back if you have F inverse of F or F of F inverse. Okay, so both ways, you can see that it satisfies the condition here of the inverse of a function. Okay, so now exercise. Let's state the inverse function of the following two functions intuitively. Okay, that means we try not to go through the math lah. Okay, of course we can go through the math and then get it, right? No issues, right? But we can actually get them kind of intuitively. So you see, this function is just a linear function, right? Kx. So you just take whatever input x multiplied by k across. So what do you think will be the inverse? 1 over k, very good. So just multiply by 1 over k or divide by k, because this one you multiply by k, what? So therefore the F inverse of x is really take x divide by k. So since you multiply by k, this one must be divided by k. So very intuitive. Okay, and certainly you can check. If you do f of f inverse, right, the kx divided by k, so you get back x. Correct what? Okay, so it should be intuitive. Now about g of x. G of x maybe not so easy. G of x is the reciprocal function. So whatever function you have, right, it will inverse. You will reciprocal it. So you give it x, right? You give it 2, right? I'll give you half. You give it 3, I'll give you 1/3. So what do you think is the inverse function? So put it another way, right, is that I give you whatever input, right, you just flip lah. Just flip. Okay? So now what is the inverse function G inverse? Any guesses? You want less intuitive? 2x? No. Half x? Okay, I give you a coin. If I give you heads, right, you give me tails. I give you tails, you give me heads. So now I want to invert that. Exactly, 1 over x as well. So you flip me, I'll flip you back. It's also 1 over x. Because remember the input, right? I give you, you flip the input, right? So how do I give you back the same input if you give me the output? I flip back the output to you. I double flip lah. I take one coin, I flip. So I get back the same thing, right? So you can check. So what is the G inverse of G? So it's going to be what? 1 over x, right? But 1 over is equivalent to the x itself, what? So correct. So you get back the original input because you flip, you reciprocal. So to get back the origin or the denominator, I need to reciprocal back again. Okay, okay? So this is using some intuition or imagination, if you will. Next. Okay, so just now I mentioned, right, if you don't have the intuition, it's fine, right? Because there's a standard process of getting the inverse function. So therefore, really, it is just a standard process. You just let y equals to the f of x. Then after that, right, you try to isolate the x. Because x is f inverse of y. Okay, you can see from the machine perspective, x is the f inverse of y. So which means from y equals to f of x, just get that x out on one side, then throw the rest of the stuff on the right hand, on the other side. So therefore you're really trying to get this. Okay? So hence, right, example. So let's say we have f of x equals to 2x squared plus 1. So you just simply let let y equals to the expression. Then we isolate this x because we want this form. Okay? So we just isolate. You can see that I bring the plus 1 across. Then I divide by 2. Then after that, take square root. Okay? So in this case, the inverse function can actually be plus or minus, because when you take square root, right, by right there should be a plus minus here, okay? But this one is dependent on the domain of f. This one I will explain in the next slide. But let's omit the negative sign, so I only have the plus sign, okay? So nothing much. So this is already my f inverse of y, okay? So x equals to f inverse of y. And this is effectively the correct answer already, okay? This is the correct answer, but because most of the case, right, they want f inverse of x. They don't want f inverse of y. Just a preference, that's all. But the function is actually the same. Okay, so therefore just replace all the y by x. Okay, but if you give me f inverse of y, right, if I ask you to find inverse function of this function f, right, if you give me f inverse of y, actually nothing wrong, it's also correct. Okay, because it's the function operation that is important, the input, whether x, y, z, w, whatever, doesn't matter. Okay? Yeah, so that's the graph of the inverse function relative to the function here. So let me explain this thing. Now, whenever you try to plot the inverse function along with the function itself, right, you're really going to observe this symmetry property. Okay, so it's symmetrical. F and F inverse are symmetrical over the y equals to x line. Okay, and there's a very good reason why this is so, right? Now, consider your f of x, which is the original function 2x squared plus 1. Okay, and because 2x squared plus 1, by right, there is a negative side. There is this side, okay? But in this case, right, let me just constrain the domain to just positive x, right, 0 or positive. Okay, now you see this guy, So what happens here is that consider a point on the graph. So what is this point? This point, let's call it AB. Okay, x equals to A, y equals to B. But what's y? Y is f. So therefore, B must be f of A. This y is f of x, so B must be f of A, as you can see from here. Okay? So now, look at the f inverse. So we have worked out the f inverse through this process, right? So f inverse is really just root x minus 1 over 2. Okay, so if you plot out root x minus 1 over 2, you'll get this graph. Okay, now if you consider a point on the graph here, right? So now imagine, at this B, so let's say B is 3. You see, y coordinate is 3. At this B, right? So this B reflected across, right? Okay, so if you have A, f of A, that means by virtue of the inverse function definition, so from here, B equals to f of A. But the inverse must be true also, what? A equals to f inverse of B. So I just changed the A and B to, I just changed the x and y to A and B. So actually the concept remains the same, okay? So which means to say, right, if my input is B, so let's say the domain, now B is on the x-axis, right, on the domain for f inverse. That means I must get back A as your output, what? Which is here. A must be f inverse of B, okay? So it works like that. So let me move this to here. So this guy, when you invert it, it's going to give you this, okay? And this, you notice, is exactly this, right? So what this is trying to show you, right, is that your A and B basically got flipped, okay? A and B basically will have flipped, right, when you talk about the function f to the function f inverse, okay? Because this is what inverse function is doing. You give it A, it gives you B, right? A will produce B. But the inverse function, right, is that you give it B, it will produce A. Okay, so this happens for each and every point along the curve. So therefore, there must be a mirror reflection, because AB becomes BA, right? It's basically reflection over the y equals to x line. Okay, so you can see example here, right? 1, 3 now becomes 3, 1. 1, 3 at this point becomes 3, 1. You see? Okay, so therefore, for any function and its inverse, you will be able to observe this symmetry. Okay, a reflection over the y equals to x line. Okay, so here comes the definition of one-to-one function. Now, for a function to have an inverse, it must be what we call one-to-one. So one-to-one means it must not only pass the vertical line test, because function must pass vertical line test, as we have discussed before. It must, in this case, also pass the horizontal line test. Why? Because horizontal line, when you reflect, become vertical line. You notice or not? This horizontal line, right? you reflect, become horizontal, become vertical line. So in order for f inverse to be a function, so your f must also pass the horizontal line test. So therefore, this means that the function must be 1 to 1. 1 to 1 graphically just means that, right, for any particular input of x, you must have a unique output of f or y. Okay, so how does this compare against the non-1 to 1 function? So non-1 to 1 function, right, will be something like that. Let's say something that looks like that. So this is not 1 to 1. Not 1 to 1. Okay, because you can see that any horizontal line is going to intersect the function twice. So this is not 1 to 1. Okay, and if you think about it, when you have something like that and you try to reflect across the y equals to x line, then you get violation of the function definition. Let me show you. Hold on, let me compress this a bit. So your y equals to x line is something like that. Okay, y equals to x. So if you reflect this across, you notice what you get. You get something maybe that looks like that. So how is this a function? It's not a function. Why? Because you're going to intersect 2 times. Okay, so whenever you have not a 1 to 1 function, right, the inverse doesn't exist. So f inverse not defined. Okay, so this is f. Can So therefore, the condition is that it must also pass the horizontal line test in addition to the vertical line test. Okay? So therefore, let's take a look at these few examples to demonstrate. So which of the following functions is 1 to 1? For those that isn't, how would you constrain the domain such that it has an inverse? Okay, so let's talk about x cubed. Is the function 1 to 1? So x cubed, by now we know that, right? It's going to be looking maybe something like that. Something like that. Correct? So this is my f of x. So is this 1 to 1? The answer is yes, right? Okay, because it is going to intercept any horizontal line is going to intercept the function only once. Okay, so the answer is yes. So yes. Okay, so it has an inverse, and in fact we can simply just kind of draw the inverse from here quite easily, right? So the fella, right, the inverse is going to look something like that. So it's going to get reflected across the y equals to x line, something like that. Okay, so this is my f inverse. But I suppose you can guess what's the f inverse. Very good. Cube root of x. Okay, so you can see this one like raising faster and faster. Then the cube root, right, is raising slower and slower because it flattens out. Okay, right, and indeed, this guy is a reflection over the y equals to x line. Okay, so the reflection line maybe looks something like that. Okay, of course my drawing not perfect. Okay, but roughly I think you can see the symmetry. And then the same goes for g. So you try to sketch out g a bit. So 1 over x squared, right? So what's the deal with 1 over x squared? Now 1 over x squared is actually not a 1 to 1 function originally. Because 1 over x squared is like that. So as x increases to negative infinity or positive infinity, right, the fella is going to be declining because it's reciprocal, something like that. Okay, so that's my g of x. So this is not 1 to 1. So the answer here is no. Okay, but how can you make it 1 to 1? You simply can just consider the positive or negative domain. Okay, so basically constrain x to less than 0 or x to more than 0. Okay, because when you have either one of them, right, then you really can pass the horizontal line test. Okay, so let's say if you constrain x to more than 0, let's say this green expression here, right? So therefore you can see that now this is 1 to 1 already. Now if it's 1 to 1, right, then you can really do an inverse. Okay, so the inverse is going to be maybe something like that, and then the inverse will look maybe something that looks like that. Okay, not very nice, but I think you get the idea. So this will be my G inverse. Okay, for this particular G, for the green G. Okay, so if you do this g, you do this g, right? Then you get here. So we can also say that if this is less than 0, then this part will be less than 0, right? So maybe I call this the orange g of x. So it's also 1 to 1, okay? But then if you want to get an inverse, right, then certainly you'll get something that looks maybe like that. So this red one will be the g inverse for the orange g. Okay? Because it is also reflecting across the y equals to x, ma. Okay, then what about h of x equals to sine x? So if you look at your graph here, it's quite obvious that sine x is not going to be 1 to 1 because it's periodic. Correct? Can certainly constrain the domain. Okay, constrain the domain to, for example, pi over 2. So minus pi over 2 to pi over 2. Why is that so? Because it is beyond this interval that you fail the vertical line test. Because, the horizontal line test. You see, here, right? Like that, fail, ma. Correct not? But to make it pass, you really just have to erase away this part. So if you erase away this part, then you notice that it will pass. Okay, so this guy is pi over 2. This guy is minus pi over 2. Then 1 to 1 already, what? Because you only can cut the fellow once for any horizontal line. Is that right? Okay. So with that, right, then you can get the inverse. So if you reflect across the y equals to x straight line, right, you also can get the inverse. Okay? Wait, okay, my drawing a bit lousy. Okay, but I think you get the point. Okay? So like that will be passing 1 to 1. Okay? So those are the conditions for a function to have an inverse, right? So in many cases, you have to constrain the domain, right? So then let's talk about the range and domain for inverse functions. So this one is easy to understand. Now because there's a reflection, so you can see that the domain for f becomes the range for f inverse. Because this guy, right, gets reflected across. Okay, then the domain for f inverse is actually the range of f. Because there's also a reflection, right, of the domain and range since you are reflecting the whole curve. That makes sense. Okay? So therefore, you should not evaluate the domain and range of f inverse independently as well. Because f inverse depends on f. Just like earlier on, right, we mentioned that the domain and range of the composite function, you have to analyze from the what? From the constituent functions. Okay? So in the same vein, this is saying the same thing. So let's take a look at this example. Suppose to determine the inverse of root 1 minus x and its domain and range. Then the question is, are they the same as that evaluated independently? Okay, so we're going to see a contrast between the two domain and ranges. So let me demonstrate. So find inverse, right? So the process has been illustrated just now already. So we just let y equals to the root of 1 minus x. Okay, then we want to isolate. So now isolate x. Because you want to get x equals to f inverse of y, ma. So therefore, this is really easy. So you just square both sides. Then after you just bring the x across, bring the y square across and the minus x across. So you get 1 minus y square. Okay, so indeed, so after you have this x isolated, right, this guy is really the f inverse of y. Because you can see there's a y variable inside the expression. So therefore, it's a function of y lah. Okay, so actually this is the correct answer already. This one legit already. Okay, but you want to follow the standard process, right? So we have f inverse of x will be 1 minus x squared. So basically just change all the y to x. So standard procedure for getting our inverse. Yeah, so therefore let's look at the domain and range. So see this guy, so original function f, right? Domain of f is, so what's the domain of f? So 1 minus x root. So which means that your 1 minus x must be more than and equals to 0. Okay, so domain of f is 1 minus x must be more than or equals to 0, right? So which is actually x must be less than and equals to 1. So that's the domain for f. Okay, cannot be more than 1 now, or else the fella give you negative argument. So root cannot work. Then the corresponding range of f is root, right? So therefore you have y that is more than or equals to 0. Okay, so maybe I use, okay, let me just use this notation. Okay, maybe just stick to this notation. Can, okay, so therefore, what is the range, what is the domain of f inverse? Domain of f inverse. So the domain of f inverse, right, you do not analyze the domain from here. Because if you analyze it from here, then you're going to get R. So previously we mentioned, basically the domain and range sort only what? So which is what we're going to do here. So domain of f inverse is exactly just the range of f. Just sort. Okay, then the range of f inverse is basically the domain for f, right, which is x less than or equals to 1. So maybe I put it as minus infinity to 1 inclusive. Okay, so you can see the swapping going here. Okay, so the thing here is that, right, when you have an f inverse, you must understand f inverse comes from f. Okay, so therefore, as you have this mirror reflection about y equals to x, not only the whole curve is mirrored, the domain and range also will be mirrored because the whole curve is mirrored, right? So you can see here, domain, right? As you mirror across, it becomes range. Then as you see the range of f, as you mirror across, it becomes domain. Agree, yeah? So which means to say that, right, really you just have to swap the domain and range for f inverse. Okay, so from here, if they ask me to analyze the domain and range of our f inverse, I cannot just analyze this thing. I might have to analyze f first. So the domain and range is analyzed from root 1 minus x. Then in order to get the domain and range for f inverse, all I need to do is to swap. Range become domain. Domain become range. Is that right? So now, what happens if you try to analyze the domain from here directly? It's wrong, right? Domain of f inverse directly, the domain of f inverse is R. Because 1 minus x squared, x can be anything, what? You can still calculate 1 minus x squared. But isn't this not correct? This is wrong. Because if the correct one is here. Is that okay? Okay, now, so the range is also, so the range of f inverse is, so what's the range? So the range in this case, right, will be 1 minus x squared. Okay, the range is the same, but the domain is not. So not the same, not the same as above. Okay, so this thing is wrong. This thing is not correct. So I'm going to show you in Desmos, because Desmos also understand the conditions of a function and its inverse. Okay? So let's look at the graph, which is 1 minus x. You see? 1 minus x. So can you plot f inverse? The answer is yes. Okay? So f inverse of x. Okay, let me just put this as maybe say f underscore inverse lah. Give it a name. How come it doesn't work? Hold on, let me just redefine. See? It used to work. Okay, let me re-enter the whole thing. F is a function. Try using all parentheses. Hold on. Okay, it could be like that. This whole thing inverse. Let me see if this is legit. No, it's not legit. Okay, that's a reciprocal. Okay, for some reason, I can't get this to work now. Okay, never mind. Never mind. This used to work. Okay, never mind. This one I'll get it sorted out and show you guys again. Right? Okay, good. So this is about inverse functions. So now we're going to use the understanding on inverse functions to define other functions that we have not defined yet. One of which is the log function, logarithmic function. Okay? So the logarithmic function is actually the inverse function of the exponential function, because we have gone through exponential function before, right? Which is just the input, right? You put into the exponent. That's why it's called exponential function. So you have some variable x, the input, okay, feed into an expression whereby you have some base a, right, that is positive, and then raised to the exponent of the input x. Okay, so what is the inverse of that? Now the inverse of that, right, is given the name. It's just a name. Okay, the name is actually the log function. The log function. So essentially what the log function is trying to do is that, right, hey, I give you a number. I give you a number. Okay, then I give you a base a. Now I'm asking the question, right, by what power must you raise the base such that I will get the input y? I repeat that again. Let's say, for example, I give you a number which is, say, 8. Okay, let's say I give you 8. You say, hey, my input is 8. Put an example here, 8. Okay, let's say y equals to 8. But I must give you the base also, because you ask me, right? I mean, what is the exponent that you must raise the base 2 to get 8, right? So therefore, I must give you the base also. So, for, let's say, base a equals to 2. So then I'm asking you, what is the exponent? What is the exponent, the power? Then you just think, oh, okay, base is 2. How do I get 8? So 2 to the power of 1, 2 to the power of 2, 4 to the power of 3, 8. Bingo. That's the answer. Okay? So what is the exponent? The exponent is 3. So x equals to 3 in our example. Okay? Since 2 to the power of 3 equals to 8, which is the input. Okay, so the log function is exactly doing this, right? This is what the log function is doing. It's really trying to give us the exponent back for a certain value. That's all. Okay, because for some reason, right, I realize that many students are not comfortable with logarithmic functions. So if I give you 16, y equals to 16, base is 2. Then you must tell me 2 to the power of 4 lah. So therefore x is 4 lah. You see here. Then if I increase the base to 4, then you must tell me it's 2 lah. Because 4 to the power of 2 is 16 ma. Is that right? Okay. So the logarithmic function is actually the power extraction machine. Okay, if you will, I mean if you like, right? It's really extracting that power. What is this power? Okay, and because they are inverse function, right? Meaning to say the logarithmic function and the exponential functions, they are inverse functions. So if you plot e to the x, you see this nice curving up line. Okay, therefore reflecting across y equals to x, you will see this ln x. So the ln x, as you can see the mirror reflection very nicely. Okay, so ln x, right, must be from more than 1 onwards, positive, the domain. Okay, the reason is because the range for e to the x is 0 onwards. 0 onwards. Okay, so therefore that range becomes the domain for ln of x. You see, it must be 0 or positive. So domain become range become domain. The same thing lah. Okay, so in this case, right, because we always use the natural base e, so the number e is 2.718 something, and we'll talk about this e more in the next topic on limits, right? So if you have inverse, then it's really log base e lah. Log base e is what? Ln, no? So just abbreviate to ln. Really, it's just log of some funky base, 2.718 something. Okay. So this one we will elaborate more on limits. But what's important now is that I just introduced the log function, right? Which is really just the inverse function for exponential functions. Okay. Yeah. So then we have the laws of logarithmics, which is similar to the laws of exponents. Okay, so this one I won't go through in too much detail lah. I'll leave you to check out the exercise, right, proving. But you must understand this. I mean, you must know how to make use of this. Okay, so maybe you want to have the laws of logarithms written down in your formula sheet. Okay, so log of xy will be log x plus log y. Okay, so you can see this multiply, right? So become plus. Very nice property. Then this division, right, become minus. Can Then this one can bring, this is one of the most important property. So you can bring down this y here. You see, this power, right? Whenever you have a log, then a number raised to some power, you can bring down the power down. You bring down this power. You see, okay? So this is one of the very, very good properties, okay, which we will extensively make use of later on. Then this is what we call a change of base. So you can see log base A, right, x. If you want to change to log base B, it's really just log base B log base B x divided by log base B A. So it's almost like you put a log base B, right? Then you put the x on top, A below. X on top, A below. Is that okay? And so every one of them can be proven easily using the laws of exponents. So laws of exponents we have seen before, okay, few slides above, right? So maybe I'll just show you how easy it is, right, to prove one of them. Okay, so maybe I'll just prove C lah. Okay, because this exercise is supposed to do yourself, so maybe I just demonstrate one and then you can try the rest. Okay, so you see this one, log base A x to the power of y. Okay, so first of all, you have to decide which law of exponent you need to use. Okay, which is the law of exponent you need to use, right? So the key thing is like that. So now this is the left-hand side, So which means that if I want to invert this, right, I will just take A raised to the left-hand side. This base A raised to the left-hand side. Then obviously this is A raised to this whole thing, because this whole thing is the left-hand side, right? Let me just label left-hand side. Okay, so it's A raised to the log base A x of y. But A and log base A raised to some power, exponential function. Log base A, inverse function of the exponential function. So therefore, this whole thing is going to cancel off. This whole thing is f of f inverse. Agree or not? Because exponential and log, they are inverse functions, right? So therefore, if they cancel, what must you get? You must get back x to the power of y. You must get back the input. So x to the power of y. Is that right? So then, if you can raise the left-hand side from base A, you must also do so for the right-hand side and see if both are equivalent, because you are trying to prove this equality. Okay? So I call this the right-hand side. So therefore, you can check A to the right-hand side. So I'm using the law of indices here. Law of exponents here. So it will be A raised to the y log base A x. So then if you look at this guy, A to the y, A to the log base A x. But this is just, wait, let me see. So all I need to do is just flip. Just trying to make it really clear here. Okay, so you can see, so this is y times log of base ax, so it's really, I just bring this y across. So multiply by y, because this is multiplication, right? Y times this log, okay? But this part, as we mentioned, right, is f of f inverse again. So f of f inverse again. Okay, so therefore this whole thing will cancel, and therefore you get the x as your input down. So therefore this becomes x to the power of y here. Is that right? Okay, so this part is just like this part. Exactly the same. Okay? But because this is a multiplication, so therefore I can bring the y over the right hand side. Right? Because it's commutative. Okay, so A times B equals to B times A. That's what I'm saying. So therefore this, you'll bring down x. So it's just like same thing, x to the power of y, you bring down this whole input. Okay, so therefore you might observe that they are the same. Okay, so therefore it shows that left hand side equals to right hand side. Is that right? Because A to the left hand side equals to A to the right hand side, you can see here, the same thing, right? So therefore it must be such that, right, left hand side equals to right hand side. Yes, exactly. Very good. I have a good question from this student here. Right? So based on what is observed here, right, it appears that a to the log base a, that means regardless of what a is, a to the log base a will always cancel away. The answer is yes. Okay, and this is from this expression here, because the log machine, right, we have already defined it to be the inverse of the exponential machine. So let me just write down the general expression. So this guy, right, y equals to a to the x. So what is the x? X equals to log base a of y. Okay, so if you combine the two, because they are inverse functions, right, so we can write down already. So therefore, x equals to f inverse of f. So this one equivalent to, so f inverse is log base a. So if you have log base a of a to the power of x, correct? Correct now, this one log base a then this one f but f is a to the x so you just sub in. This guy, you just get x, there, this x So which means, like, virtually, right, you are just cancelling away this thing. You're really just cancelling away. Right? So you're only left with the x. So therefore, this must be equivalent to x. Okay, because what's the thing about inverse function? Right, you must get back the original input. You see this original input x, there you get back the original input correct or not? So therefore it's like virtually you cancel this thing okay, so that you get back the exponent x here, because that's what I want, okay, so what he's saying is correct and then the other way is, right, y equals to f of x. But what's f? A to the power, right? But x is this log base a y, log base a, in this case log base a x I just use x. So that means virtually I'm also cancelling the a to the log base a. Hold on let me use f inverse instead, so this will be clearer, okay? So f, right, is a to the power of, then the f inverse of y, right, is actually log base a to the power, log base a of y. So virtually I'm cancelling a to the log base a. Then I just get back y, which is the original input in the second expression. You see? X, I get back x. F inverse of f. Y, I get back y. F of f inverse of y. I mean, x or y doesn't matter. Okay? But what's important here, right, is that log base a to the a. This one cancel off. A to the log base a cancel off also, because they are inverse functions. Any other questions? Did I answer your question? Okay, so it doesn't matter what's base a lah. A can be anything, but must be the same lah. Okay? Yeah. Yeah, so I just did one. You can try out the rest. This one I'll leave you to do the rest. This one. This one. Why? Okay, be careful here, because his question is, right, if I strike this off, isn't this x times y? No, because this x must be brought down to be the base. This one remains as a power. Okay, wait. I better put a bracket. So it's like that. Let me put a bracket so that it becomes clearer. Is that okay? Because this y, I understand, this y is multiplied to log ax. I understand. Okay, but you have to treat this whole thing as one item. So this whole thing is going to return you x. So it becomes x to the power of y already, It's not x multiplied by y. Because it's not like the whole power being brought down. It's this x being brought down to be the base, that's all. This whole thing, right? Because you see, this whole thing you cancel off, right? You get x, there, this x all. Then the y is still the power, You cannot anyhow bring down y, Okay, any other questions? Good. Sorry, I have to push on, Okay. Yeah, so I'm going to leave you to try out some of the questions, and maybe I'll just solve the harder ones. Harder ones will be, I think, C and D. Okay? So this one, DIY, because the answer is given there. If you cannot, right, then I'll go through during the class tomorrow. Okay? Do it yourself for A and B. C, I'll go through with you. So now, without using a calculator, solve the following. So basically, it's trying to test you on the understanding of using log expressions. So this is actually not that difficult also, because you are trying to use the property of logarithms here. Now, if you look at this guy, okay, you look at this guy, right? You can see this 2 here. Now, obviously, the 2 can be brought up, right? So it really becomes ln x minus 1 plus ln root x square. Okay, but root x square is just ln x, what? It means the net result is ln x minus 1 plus ln x. Okay? But then if you look at this ln x minus 1 plus ln x, plus. Plus. So plus become the arguments multiply. So become ln, big bracket, x minus 1 times x. Okay? Of course, I'm using the first law here. So therefore, it's really x times x minus 1 equals to 0. Or am I wrong? Hold on. Is that right? My answer is 1 plus root 5 over 2. Correct. So therefore, this ln, this thing, right, equals to 0. But I'm trying to solve for x there. So what I must do to get rid of the ln, okay, let me put the 0 on the right hand side here. Okay, so now you look at the last expression. How do you get rid of this ln? You have to e. Because the inverse of ln is e, e raised to the power of something. So therefore, exponentiate both sides. E to the power both sides. So therefore, you get e to the ln. E to the ln of this nice expression, x times x minus 1. Or you can put it as x squared minus x, just multiply out, and equals to e to the power of 0. So therefore, e to the ln, inverse function, base e and natural log, inverse function. So therefore, x squared minus x, the argument, right, must be brought down. E to the 0 is 1. Okay, so therefore you have a quadratic expression. So because you want to solve for x, so therefore you got to solve for the roots of x squared minus x minus 1 equals to 0. Is that okay? So then this is not factorizable into integer factors. Okay, you can't factorize the minus 1 such that you get a minus x there. So therefore I'm going to use the root expression. So x1, 2, right? Or rather x equals to minus b. So become 1 plus minus root b squared, which is minus 1 squared. So let me put minus 1 squared minus 4 times a times c, which is minus 1. Then the whole thing divided by 2 times a, which is 2 times 1 then. Is that right? Yeah, so therefore you have to work this out. You have to work this out. And therefore it's really a half plus minus, this guy looks like what? 1 plus 4. So it's root 5 over 2. Okay, but that's coming from the root formula, because root formula naturally will give you plus minus. Okay, but you have to inspect. So when it's half plus root 5 over 2, it's a positive number. So positive number, of course, okay lah, because root positive is okay, right? But when you try to have half minus root 5 over 2, it's negative. This guy is negative when you have a minus here. Agree, Okay, so therefore, root negative, undefined. So therefore, this thing, right, remove the minus. So I'm just going to put here, reject half minus root 5 over 2. Okay, so maybe I put the reason here, because you really get a negative number when you have minus. Any questions? So basically just solving using the laws of logarithms in the earlier slide, and then just trying to get the x. Okay, so there'll be more practice questions in the tutorial. So C is done. So then for part D. So for part D, right? So you can see there's a 3e here, right? There's an e to the power of some stuff here. Okay, so it certainly makes sense to just combine the power using the laws of exponents. Okay, because same base can combine power, right? So therefore from here it seems to tell us, right, to just combine the power, become e to the 3x plus 1. Okay? Then minus 4x. Oh, my bad. 2x plus 1, thanks. Okay? So that's equivalent to e to the minus 2x or 1 minus 2x then. Then this guy is 3e. Any objections? Okay, then obviously you want to get the x down, right? So it's coming back to this problem again. Okay, so this one is like trying to get the x without the ln. So you e both sides because making use of the inverse function to get rid of the ln. Making sense, huh? So therefore you want to get the x down, what do? Ln. So they can get rid of the e also. It's the same usage of inverse functions. So ln both sides then. Okay, so from here, ln both sides. Okay, so if you ln both sides, right, then you realize that, oh, my 1 minus 2x come down already. Okay, but you have to be careful here. This one is ln 3e. So of course, to make it easier, right, because ln 3e but ln 3 is ln 3 plus ln e, what? But it's like ln times, okay, sorry, it's like ln e to the power of 1. So ln e must be what? 1. So therefore, this whole thing, right, is going to give me 1 minus 2x equals to ln 3 plus 1. Because ln e is 1. If you press e is 2.7 something. So you press if you press your calculator, ln e, then you're going to get 1. Because basically the power for e here is 1. So you ln e inverse function, right, you get back the exponent. Because the exponent is 1. Okay, so from there it's quite easy to see the result already, which is just isolating the x. So it's really x equals to, so you can minus 1 on both sides. Okay, so it's really giving me half of ln 3, or rather minus half of ln 3. You can also put it as ln root 3, 1 over root 3 in fact, because there's a minus there. Okay, but I think it's okay lah, can leave it like that. Any questions? Okay, so certainly you try A and B on your own, and so as well as the practice questions in the tutorial. So now we're going to move on to talking about the rate of growth of elementary functions. Okay, so this whole thing is going to make sense because now we have defined every elementary function already. So what's elementary functions? Okay, as I mentioned before, it is just a representation of given an input x. What can you do to the input x? First of all, you can multiply by a constant, easy peasy. Okay, you can raise the input to some power n, so polynomial or power function. You can put the input x at the exponential function. Can Then you can raise the input x to some fractional power, root function. Then as we have discussed, if you have an exponential function, then obviously you can inverse that, and therefore you get the logarithmic function. Okay, so the growth rate must be in this order, right? Because mx is really just straight line. Okay, you just multiply by some constant m, so you wouldn't be able to grow very fast. Okay, it's growing at a linear or at a constant rate. Then we have power function grow faster lah. Okay, so therefore x squared. But because this x to the power of n and 1 over n, x to the power of 1 over n, right, they are inverse functions. Correct or not? Power function is the inverse for root functions, Root function is the inverse of power functions, what? So because they are inverse, right? So power function, you inverse, become root function, So therefore you can see that this guy grows the second fastest. So this guy, as compared to linear function, right? So this guy, right, must grow the second slowest. Second fastest, second slowest. Because there's a reflection, okay, about y equals to x. Then finally, exponential function grows the fastest. Okay, so therefore, the inverse function must grow the slowest. Because, once again, reflection over y equals to x. Okay, so therefore, there's a natural growth rate to the elementary functions shown here. Okay, and take note that some of you may think, right, oh, power function, if I give a very large power n, right, like x to the power of 100, then don't tell me this is going to grow slower than a small base raised to the power of x. Your power very big, what? This power so big that it overpowers this exponential function. I mean, that sounds logical, what? Because I can give a very super big power. The answer is the exponential function is always the fastest growing, no matter what is the power. Okay, so I'm going to quickly demonstrate here in Desmos. So let's say you get 2 to the power of, okay, 2 maybe, okay, let's consider x to the power of 10. You see, x to the power of 10, wow, shoot up very fast, what? Correct or not? You see, it shoot up very fast, Then what about, like, say, 2 to the power of x? So this base only 2, Correct or not? So you can see this guy doesn't grow so fast, what? Like, for example, this one already shoot to don't know infinity already, right? But this one is still growing slowly, like 6, then 8, and so on and so forth. So from here, it doesn't look like this 2 to the power of x, right? It's going to be bigger than x to the power of 10, okay? But you have to look at the big picture, right? So what's the big picture? Big picture is that you must zoom out, what? So zoom, Okay, I hope I can do this before the class ends. Okay, I mean, yeah, it's going to intersect soon. Okay, see what I mean? You see? So eventually, the x is not even very big, like almost 60. At x about 60, my 2 to the power of x already overpower the x to the power of 10 already. You see that? So there's always a crossing point, right? For some big x, exponentials will always be bigger than power functions. Okay, so that is no matter what's the base. Of course, you cannot tell me this base is less than 1, must be more than 1. Okay? Okay, so now we are going to look at inverse trigo functions. Yeah, still have. So, because just now we inverted the power functions, we inverted the linear function, and then we also inverted the exponential function, but we haven't inverted the trigo function yet. Okay, so trigo function is what? Projection functions. This one we mentioned before. Right, so what's cosine x? What's cosine theta and sine theta? Adjacent projection, opposite projection. Correct, I mean, just in case you have forgotten what was the projection machine, right? So this is your hypotenuse, okay? So what is your x? Your x is this guy, cosine theta. Theta is the angle. Then what's your y? Your y is sine theta. Then the hypotenuse is 1, okay? So this is your projection functions, projection machines, x and y. Okay, but then we ask the logical question. You give me the angle theta, and then I can go through these projection functions, projection machines, and then I can output the coordinate x or y. Okay, this one we know. But what if I give you the x and y? I give you the x and y. I want to compute the input theta. So can I do that or not? Of course I can do that, right? So therefore, there will be some inverse trigo functions being defined. Okay, so you can see from here, right? So to get back theta using sine, I have to have a sine inverse. So I just sine inverse the y, this y coordinate, right? I'll be able to get back my theta. Okay, the same thing. I can also get back my theta if I'm using cosine. So I just have a cosine inverse. Is that all right? Okay, so cosine or cosine inverse will be just giving back your original input. Okay, same thing as sine of sine inverse. Can Okay? So therefore, these are the inverse trigo functions being defined, right? So you can see the graph from here is exactly the mirror projection that I didn't manage to draw earlier on because of my lousy drawing. So you can see the sine x here, the red color graph, okay? Nice sine x function. So as we mentioned, right, if you limit the domain to minus pi over 2 to pi over 2, you have a 1-to-1 relationship, and therefore you can do the reflection. You get the sine inverse. Okay, so certainly this is obtained from Desmos, right? So you can see the really nice symmetry there. Okay, so that's for sine, and then this is for cosine. Okay, so this is for when you invert cosine. You see, right? And of course you can invert tangent as well, right? You see it's a tangent. The red color curve is the tangent, so you can invert, right? You just reflect across y equals to x, and you get this nice tangent inverse theta, or tangent inverse x. Okay. So you might observe that all the domain and range, they get swapped. So this one we mentioned before. Okay, so you can see, sine, right, is the domain. Then domain become range. So this domain becomes the range. Then the range of sine becomes the domain of sine inverse. Okay, so there's an exercise here which is, without using a calculator, state the value of sine inverse half. So actually this one a bit of a visualization question. Okay, so what's the deal here? The deal here is that, you really just need to draw, okay, the quadrant. Then because I want theta, because sine inverse is going to give you angle. So, but then what's half? Half is the projection. So this half is the length of the projection, right? Because half is it's here lah. Okay, so this is half. But if you move this projection here, so then where's my hypotenuse? My hypotenuse is here. Okay, so I purposely draw it like that because I know that, right, this guy is a 1. My hypotenuse is of length 1. But my opposite is of length half. So it must be something like that, right? I mean, half to 1 is about this ratio, as I've drawn here. Okay? So which means sine inverse of half, I want to know what is this angle theta. Okay, you can see this one is twice the length of half here. Right? My drawing should be pretty decent here. Okay? That means to scale. So therefore, what do you think is theta? 30 degrees, very good. Okay, so I mean just visual inspection. So that means the theta should be 30 degrees. 30 degrees is pi over 6. Okay, so this is answering the question. Is that right? Okay, of course you can verify yourself pressing the calculator. Okay, so then, so cosine and inverse, inverse, cosine, inverse tangent, I leave you to go through yourself. Okay, now final part, which is on the transformations of functions, right? So this one is actually quite easy to understand, okay? So I'm just going to quickly go through, Right, so the graph of some functions can be obtained by transformations from the graph of the basic function. So if you have a basic function f of x, and you want to get y of x by shifting, so shifting is really just plus c and minus c, so this one very easy, Okay, if you have plus c where c is positive, then you just move up lah. Okay, let's say c equals to 1, right, you can see, move up the whole graph, right, by 1, so y-intercept change from 0 to 1. Now obviously you can shift down as well, so shift down, right, minus c, so c is 2 for example, right, so minus 2, so you just shift down the graph entirely by 2 units, simple as that. Okay, then the thing about horizontal shifting is this. Now horizontal shifting, right, you have to go and mess around with the x instead of the y, because when you plus c minus c to the y value, you shift up and down. Okay, makes sense. But if you want to do horizontal shifting, then you are going to change the input x. Okay, change the input x. So now, originally, you have f of x, where the input is x, right? So if you want to shift left, you plus c. Okay, there's no typo here. You plus, you don't minus. So which means that it's the opposite of y. Okay, and why is that so? Because when you plus c, what does x has to be to give you the same function output? Now think about it. Let's say this x is 2. Let's say this x is 2, f of 2 let's say. Function value is f of 2. Okay, I go and plus 1. Now x become what? To give you the same function value. X must become 1 what? Okay, let me write the example here. So let's say this x is 2. Then I say, hey, I want x plus 1 now. So then you must tell me, then my x must be 1 what? Cannot be 2 anymore. So what does that mean? That means your x has reduced. So if your x has reduced, the whole graph must shift towards the left. Isn't this legit? Okay? So now you look at x square graph here. You see x square graph? So let's say now I want to get the function value at 1. Okay? Function value at 1. So what's the function value at 1? F of 1 equals to 1. You see? F of 1 equals to 1 for x squared. Now look at the new function. Now this one minus 1, right? How can I get 1 back? I must make my x 1, right? So therefore, if I have a minus, then my x will increase. If I have a plus, then my x must decrease. Okay? So therefore, this is the same function value as when x is 1 here. So therefore, you can see that this x must be what? 2. Because 1 square So this x must be 2. So when this is a 1, this is a 2. Because it's a minus 1. To get 1 square. Okay, so I'm really comparing these 2 points here. So therefore, because x must be 2 instead of 1, right, as compared to x squared, the whole graph shifts towards the right-hand side. Okay, so this is what I'm trying to demonstrate, shifting towards the left-hand side when you have a plus. When you have a minus, then it shifts towards the right-hand side. Okay? So this is what this explanation is about. Right? So if you don't understand this, then, I mean, you can obviously just put this inside your cheat sheet and then refer to it directly. Okay? But it's good to understand why is it that when you have plus, then it's actually shifting left. Yeah, that's why I got 8 pages, right? Okay? Yeah, so let's look at vertical scaling. This one easy to understand. Right? So if you have a graph, f of x, and you know scale it. So scale it can scale it like stretching it vertically. So if you stretch it vertically, you just multiply by c, which is more than 1. Right? So for example, e to the x, right, become 2ex. You can see the whole thing stretch up. Okay, then if you have a decimal for c, then obviously you are compressing the graph. So it's like scaling by so-called compression. Okay, then the same thing goes for horizontal scaling. So you notice or not, vertical we always do to the function itself. Then for horizontal, whatever transformation, we just do to the x. Okay? So therefore, if you have f of cx, then you can observe that, right? If c is more than 1, then you are compressing. You notice the opposite, opposite case. So what's the rationale? Rationale is the same as that explained earlier on. When your c is, let's say, 2, right? Your x no need to be so big, what? Let's say c is 2. Then your x got to be smaller, correct or not? Correct or not? So when you have smaller x, doesn't it represent the compression? So you're compressing your graph horizontally when your c is more than 1. Okay? So the opposite is true also for the stretching horizontally. Okay, then this is important. This is one of the most important, the more important transformations here. Okay, and that is on the reflection, right? So this is easy to see. When you have a negative multiplied to the whole function, you are reflecting the function across the x-axis. Okay, because whatever positive becomes negative, whatever negative becomes positive. So therefore, reflection over x-axis. Then if it's reflection over the y-axis, I think by now you know because you have gone through even and odd functions already. So f of minus x. You put a minus to the x, right? You are actually reflecting across the y-axis. That means horizontal reflection. Okay? Yep. So therefore, various transformation can be combined in a function, right? So the order of transformation is as such. So this is a general recommendation, right? How do you do the order of transformations? Okay, A followed by B, followed by C, followed by D. Okay, but of course, some transformations you can do in any way you want. Those are for the easier transformations. But more difficult transformations, right, it's recommended you follow this order. Okay, so this one we will delve more into it, right, in the tutorial question. Okay, is this the last one? Okay, almost the last one already. So bear with me for another 5 minutes. So from the graph of f of x, obtain the graph of y in a step-by-step manner. Okay, so just testing your transformations here. Right, as you can see this is ln x. Okay, so step-by-step, so we follow the ABCD recommendation. Right, so what's the first one? First one is A, so AX. So from here, so I'm going to write y1. So look at the end result that you want. Ln 3 minus x, correct or not? But it's minus x, So then you have to do what? Ln x become ln of minus x. Because you want minus x here. Right? So better do the minus x first. So therefore I'm going to draw the graph and show you. Of course you can verify with decimals later on. So ln x is the input graph. Let's draw it in blue. Ln x. Okay, so this is ln x. And clearly this is a 1. Okay, no issues with that. So what about ln minus x? So you tell me how to transform ln minus x. X become minus x. Very good. Some of you show the hand sign. Okay, very good. So basically, reflection. Okay, so I use a pink color here to represent y1. Okay, so this will be minus 1, obviously. Okay, So ln minus x is done. So look at this. So this is x minus b, right? So therefore you have a b, which is trying to do the horizontal shifting. Okay, to the to the input x. So therefore, let's see what can we do here. Maybe green color. y2. So I want 3 minus x. So eventually this will be what? Ln of minus of x minus 3. Correct what? Minus x minus 3 is the same as 3 minus x. Minus x minus 3 is the same as 3 minus x. It's the same thing. Okay, so second, so basically it's second transformation, which is the B transformation, right? So what do you do when you have x, right, changing to x minus 3? This x, changing the whole x itself, becoming x minus 3. So this is horizontal shifting. So minus means what? Minus means you shift right. Okay, can? Minus. Shift right. So come back here. Whole thing shift right by 3 units from y1. So that will give you y2. So must shift until where? Shift until 2. So let me just do a shifting nicely here. Okay, I think that's not bad. So this one will become a 2. And therefore this is y2. Okay? So then subsequently you have a 2 in front. But the 2 in front is easy. So maybe y3. So 2 times this whole thing. Okay? So because you take the whole function, the ln function, the whole function, multiply by 2. So that means it must be vertical stretching. Because times 2 ma, so become bigger. Right? Okay? So this is exactly what I'll be doing here, which is just to take the graph, and then I'm just going to stretch it. So from here, okay, so stretch, okay. So when I stretch, certainly the y-intercept, the x-intercept, no change. Okay, roughly 2 times, maybe not very accurate, but you get the idea. This is y3.